Well, hello everyone. My name is Juan Andrade. I will give a talk. Well, this course on event vision for robotics. Basically, this is like a grouping of the research that is being developed here at EV regarding event vision. So this is going to be a talk consisting with a few different work from different people, and the names of the people in there are the ones that are contributing to this. So basically, what are event cameras? Event cameras are these new type of sensors. Well, not that new anymore. They have been around for about 10 to 15 years now. And these are cameras that do not process images as we're used to with conventional cameras. Event cameras, what they do is they take pixels that change their intensity value significantly above a threshold. So they just record the location where this happens. And what you get is the polarity, whether this goes up or down, and the timestamp when this occurs. And the information that is sent through the bus of an event camera to the computer is asynchronous. That is, you get not a constant rate of events, but you get asynchronous data as soon as it occurs with a lag of a few microseconds. So another thing about this is that the events are fired at logarithmic change of brightness. This is not a constant change, but it is logarithmic. So this image has been taken from the work of Scaramuza, and it shows a comparison between what you would get from an event camera compared to a conventional camera. And there are two things that happen here. On the one time, when there is no motion in the scene, you will not get events because brightness will not change at any pixel. So there is no data transmitted through the bus. And but when there is slow motion, what you will get is basically only the firing of the events that happen at a frequency much higher than you will get with a conventional camera. So this will be in the order of microseconds. And another thing that happens is that for very fast motion, when you in a conventional camera, you will get motion blur. In an event camera, you will get still the firing of the events. So this is an image of what you will get with an event camera. One advantage of this type of cameras is that they have very high dynamic range. Even when you have an image that will be saturated in a conventional camera, with an event camera, you will not have that such saturation. So using an event camera might help reduce the effect of overexposure or situations in which you have very low contrast or low lighting. Event cameras then are best suited for situations in which there's motion. If there is no motion, you will not be able to use an event camera, but not just that they are useful when you have very fast motion. When you get, as I mentioned, when you get blur in a conventional camera, in a DPS or an event camera, you will get still the list of events. So that's why we are targeting its use on applications related to robotics. So what I will talk to you today will be 4 different works regarding the use of event cameras. One is for high-speed event camera tracking, that is computing the pose of the camera when looking at an unknown pattern. And then how do you extend this to actually perform a SLAM using an event camera? And in this case, the SLAM that we do is tracking lines, or we make a map of lines. Then we're trying to figure out if the event cameras can be used also when you don't have this type of features for any kind of conventional feature. So we're trying to learn feature descriptors for event cameras, and we're also trying to estimate motion using different types of neural networks, in this case, spiking neural network. So the first of these works is high-speed event camera tracking. The idea is to track the 6 degrees of freedom of the camera, its position orientation, when you have very fast motion. And the assumption is that you know the scenario. That is, you have a set of 3D lines that you know their geometry in the world. So our scenario is 1 cubic meter, in which we have 3D lines, and we're using a Davis 240C camera. And you will get, on an event camera, you get the polarity positive polarity in red, negative polarity in blue. And you will see lots of events here because what you are seeing is chunks of 10 milliseconds displayed on the image, superimposed on top of a conventional camera image. But in reality, what you get is only just one event at a time at different timestamps. And we process all of those events, each of them when it occurs. So the structure of the algorithms as follows: you get the asynchronous feed of events. We have to do some event and distortion because of the calibration of the camera. And then we choose a window of events, and with that window of events, we do data association, and then we do the state estimation. Once you have assigned an event to a line that you have in the map, using in the image plane, using this correspondence algorithm that we explained here, then we do the state estimation of the camera position. And we do this just by tracking using a conventional camera filter. So the first part is to distort events. We use a very fast formula for the computation of the inverse radial dense distortion. This is a paper by Drap of Lefebvre. And with this, you get the undistorted image. And then, oh, hold on, what happened here? Then we take 100 milliseconds temporal window of events. We project those events to the image plane. And what we do is that we, what is going on here? What we do is that we choose those events in the image that are that would be candidates to match with some of the lines that we have in our map. So with the current estimate of the location of the camera, we project the lines onto the image, and we threshold for those areas far away from the line that we are trying to match with, and also with the crossing points of where two lines meet, because these will be regions of ambiguity. So the measurement equations are conventional measurement equations that you would use in computer vision, using standard mechanisms for that. And with that, we get matching of line events to lines, and that will give you, each of these observations will be events that you can use to update your Kalman update. So as you see, the measurement model was that, the distance from the point to the line, and the equations that we get for Kalman filter, we use different variants of filters. We use, for a camera that is moving in 3D, we could even have a constant position model in which you just use the previous position and update with the assuming Gaussian noise. Or you can have a constant velocity model in which you have the previous velocity at which the camera was moving. Your prediction is using that constant velocity model, or you can even have constant acceleration model. The thing is that each of these models means you have more variables in your state vector to update. So if you want to do it really, really fast, perhaps a constant acceleration model in which you have many variables is not that useful, and maybe constant velocity model would be enough. And then you have also two different projection models, one in which the camera is moving about a static object, and then you also might have an object that is moving in front of a static camera. So you have to consider your measurement model taking into account whether you are using one case or the other. Then there is experimental validation. Yeah, you can see here. You know your model, so you are projecting the lines of your model into your current position of the camera. And these are the green lines that you see on the left of the screen. And you have the positive events and negative events. And for this work, we're considering all of them as positive and negative as events occurring that you can match to a line. So there's no difference between positive and negative events in this sense. So with that, what we are able to do is that we are able to estimate, what is this? We're able to estimate the linear speed of approximately 0.7 meters per second and angular speed of 0.8 radians per second. And our ground truth is being matched against an OptiTrack system that we have in our laboratory. And as you can see, the root mean square error is below 1 centimeter. For X and Z, and a little bit above 1 centimeter for the Y direction. Then you can do the same thing for for very at medium speed. Oh, and I shouldn't have stopped that video on top because then you have the one on the bottom that does not match the movement. And as well, you're still tracking the position of the camera at about 1 meter per second, 1 centimeter error, 1.6 meter per second, and 5 radians per second. But this is good compared to what you will get with a tracker with conventional computer vision when you do very fast motion. For instance, in here, we're doing very fast rotations that are even not that perceivable by a conventional human, but the human eye, and still the system is able to track these very fast rotations. And in this case, we have very fast motion, the fastest that you can get with a human hand at about 7 hertz, and also changing the lighting conditions. This is turning the lights off in the laboratory. Since you have very high dynamic range with these cameras, you're still able to see the events even when the conventional image in the camera does not see anything or it's very obscure. In this case, you can still track it. So this is the faster that you can do with a human hand for this kind of camera, and we are not even getting below that true mean square error of about 1 centimeter per second. So we wanted to do it even. If we could, we wanted to do it even faster. So we said we need to build up a system in order to search for the limit of this type of system. So what we did is that we built a mechanism in order to move the pattern at an even faster rate. So with this system that we built, we were able to move the pattern at about 100 revolutions per minute. That is about 13 hertz. This video that you're watching here is reproduced at 1/10 of its actual speed. And in here, you can see that we can even track the position and orientation of the camera precisely with the event camera. And the system breaks at about 950 revolutions per minute. That's about a little less than 16 hertz cranking of the system, and about 2 meters per second and 25 G in the acceleration of the target. So there's, in our opinion, I don't think there is any other type of computer vision system that can do tracking at such fast speed. So that's a very good application for event cameras. Now we wanted to see whether we can exploit this very fast and accurate tracking in order to do SLAM. So the idea was to not just use this learn pattern of lines, but also increase the pattern of lines. And for that, we implemented two modules. One was the tracking module that you just saw, and the other one is a mapping module. The mapping module runs at a much lower speed. This one runs at about at the microsecond range, and the mapping module runs at a much lower rate, classical computer vision frame rate. So the stages in the mapping part was the ray tracing, the volumetric ray counting, line extraction, and boundary adjustment. And this follows another paper also dealing with mapping with event cameras. So for ray tracing, you will get the windows of events, and for each window of event, we will compute the central position of in the keyframe, and use this as a key reference. And you, with this, compute the key reference flows, and you will have a keyframe length of about a few chunks of keyframes. So we implemented a heuristic to do fast ray tracing, and there were 3 steps in this fast ray tracing. The first one was that we mapped all the events from all the from the cameras, from all the different poses of the cameras to the Z-plane in the reference pose using the homography. And then we mapped these points to each depth of each of the different planes, and then we did voting at each of these different depths. This is a representation of how we fill the grid for the different events in 3D. And I think there was the video cannot be played. This video cannot be played. So this is another. This is the second step of the mapping part. This is volumetric rate counting. And in this case, we use two different ways for voting for the events that counted for each of the different rates. We have on the one hand bilinear voting and on the one linear voting. What they did here is maximizing the votes of the events on each of the different lines. And then after we get that, we get the final line extraction. So these are the different hypotheses for lines that you will get for events in the window of events that we were processing. And with this masking of the images that you will get candidates for events that belong to lines, and you will do Hopf transform to compute the actual parameters of each of the different lines. After the Hopf transform, you will do some merging so that you get larger lines, and you will do some also runtime removal of outliers. And you will, in the end, have a list of different lines that you will want to add to your global map. So this will be, for instance, the lines that you will add into the map. There are also some heuristics to add lines to the global map compared to the previous lines that you had. And there are two different comparison criteria that you would use to pick out in computer vision. One will be the perpendicular displacement of the line. The other one will be the angle of the line with the new one. And in the end, once you have all these lines and the parameters of these lines, you will do some bundle adjustment to optimize the location of the lines and also the location of the poles. And you will do this at the rate of the mapping submodule. So this is a video. I don't think so. Yes. This is a video that shows some results of the mapping part. And here you are mapping only lines that are on one of the planes, and after that, you will start looking at lines that are on the other parts of the scene, and you will continue doing the 3D mapping. Then I'd like to stop this part of the presentation here and show you newer videos of this. So I will do this. If you don't mind, I will show you. There's one problem with this, in that you need to do the bootstrapping. That is, in the beginning, we used some part of the pattern as a known map to initialize the tracking, or initialize the mapping and the tracking. But sometimes you do not have even in situations, there are situations when you don't even have this original part. So we will do some bootstrapping to learn this initial part. So one way to do it again was using Hopf transform and do the conventional line tracking using these Hopf transforms. And in this, we will do this, we will learn this initial pattern. And once you learn this initial pattern and you do this bundle adjustment to learn this initial pattern, then you will have an initial camera pose and the initial part of the map. And from there, you could continue the rest of the process. So this was for bootstrapping the mapping part. And then I have another video I want to show, which is the final mapping of a different larger scene than what you just saw there. In there, you just saw 1 cubic meter area. And in this one, you have a larger scene in which you have a few desks in an indoor office, all cluttered with different objects. Of course, all these objects have to have straight lines in order for our system to work. So in here, you can see the tracking module leaving a trail in black, and you will see the results of the whole mapping part, and you can see that the structure is accurately estimated. You could turn off the lights in the laboratory, and the mapping and tracking system, because of the properties of this type of cameras, will continue. as before. So in this case, this is the SLAM module working in a scenario of about 20 square meters, more or less. Okay, after that, let me see. Well, this was another previous result of the tracking. So after that part of the SLAM, that part of the SLAM, what I will talk about now are two other problems. One of them is one of the drawbacks of the system that you just saw is that we're using conventional lines, and it is only useful in scenarios in which you have very prominent straight lines. But what if we could do it in a more general scenario, one in which you don't have those type of handmade features? We would like to learn the features from scratch, and for that we're working on a problem which is feature learning using CNNs. So there are different ways to represent aggregated sets of events, and the one most popular one is the surface of active events. That is, in a small period of time, you record all the events that happen close to a different location, to a particular location, and what you will get is the surface that is made by aggregating all those events compared to a pixel. So that's the most popular one that is being used. Here you have different comparisons of different types of representations for event aggregation, but as I said, the surface of active events is the most popular. Then there are some descriptors that have been described in the literature, and these descriptors are basically trying to mimic what is done in computer vision, trying to extrapolate this into the event cameras. So there are event corner detectors or even event descriptors. And our approach is a little bit different. Our approach is try to learn which are the events that are most representative for a particular task. In this case, for mapping, this is what we want to do. So what we do is that we're generating triplets of surface of active events, and what we do is that we train a CMS network in order to learn these events, and then we evaluate the different descriptors that we get. In this CMS net, what we do is that we give positive reward to the events that match the ones that are consistent with what we want to track or recognize, and then with negative for the ones that are not. So for that, we need to create synthetic data sets of events, and this is one example of how we create these synthetic sets of events just using conventional images. And then what we need to do is to build surfaces of active events for several motion directions, and then use ORBs detected on the texture. So for each of the ORBs detected on the texture, we build the surface of active events related to these ORBs. These are the features that we're learning. So the one important thing about this is that the surface of active events are motion direction dependent, and also speed dependent, although there are some descriptors for surfaces of active events which are velocity independent. They are normalized with regards to velocity. There are still no representation that is motion direction independent. So whenever you build a representation of features for tracking with event cameras, you will need to take into account that all these representation of the events of those locations are different depending on the direction of motion. So as I said, what we do is we learn the event description using a CMS network. And what you can see here is the results of using these only surfaces of active events, or using the learned descriptors in matching features. So as you can see, using the learned descriptors, we have less error in matching the points. This is also a representation of that using ROC curve of the learned descriptors compared to using simply the surfaces of RP events. As you can see, we have a little bit better ROC curve characteristics using our events. Then the last thing I want to talk about is using spiking neural networks to compute optical flow. So the problem in here, the statement of the problem is that we want to understand how these spiking neural networks work and whether this can be useful for motion estimation in robotics. The idea is that spiking neural network is a network that processes events or processes the firing of the neurons asynchronously, just as what happens with the event cameras. So this is why we think that these are a type of network that is best tailored to be used with event cameras. So the neuron model that is being used is a modified version of the adaptive link integration and firing model. In this model, you will get, as you can see in the left, these are firing of neurons in a previous layer. And in the initial layer, it will be just one single input, which will be all the events taking place. So what you will get is the firing of the events. So in a neuron, what you will get is the aggregation of the firing will do just as it does in an event camera. That aggregating all the firing of the neurons will, when it surpasses a given threshold, then it will fire the next neuron. But another thing that this neural model has is that it has a refractory period in which if there is still firing of the neurons in the previous layer, they will not be taken into account. This is a refractory period. And also what you will get is some homeostasis using that. And then the learning rule that is being used is the STDP learning rule. So there are other comments here about how these different neurons firing compete for the next neuron, and there is this we need to take into account local interlateral competition. So for this, we also use some conventional data sets that are already available, and we also implemented our own data sets. So these are two different data sets that are already in the literature, and we have implemented also our own. The architecture that is being tested is something like this, in which you have basically three very important different layers. One is a convolution layer, which will produce local features, local motion features. And then you will have a merge layer, and then another convolution layer, which will have layer local features. And then for that, from there, you will have a pooling layer. And in the end, you will get a descriptor, which give you the estimate of the global optical flow of the scene. So these are samples of what you will get. For instance, this is the input layer in which you have the events, and then you have the first layer, the convolution layer. Then you will merge all those events, and you will have next layer, and you have this convolution. As you can see in this convolution layer, you will get different features representing different direction of motion. And in here, the color means the direction of motion. The color means the kernel that is being fired, and it will represent a different specific direction of motion. And then from there, you will get the pooling. And when you combine the pooling of all these events, you will get a dense estimate of the direction of motion. This was using the roadmap dataset that I showed. And this was using the rotational disk dataset that I showed. Well, here are the layers are a bit more explained. This is the single synaptic convolution layer that I talked to you. And then this is the convolution layer again. At the end, in the pooling layer, where you get this special dimension collection, of course, because we're reducing to from all the different, you have the list of the number of kernels here with the dimension of this pooling layer, and in the end, you will get just one estimated direction of motion. This is a video of initial results for that, in which you get the input layer data, you will get the local motion field. This is result of the first convolution layer, and you will get the results of the second layer, the local motion field here. And what you get is the aggregation of these local motion fields here, in which you have an estimation of motion. And in this case, we are doing constant velocity diagonal motion, and you will get the estimates on the velocity for the translation in X and translation in Y. And of course, there's no motion in Z. And this that you are seeing here at a very low speed, in reality, corresponds to a very small window frame of. In here, you have already passed like 200 milliseconds. This is about, I don't remember how much it was, but it is 2 seconds, right? So we are, this entire video is a 2-second chunk of data. And this 2-second chunk of data, we can estimate fairly accurately the velocity of motion along the X and Y direction, perpendicular to the image plane. In this case, using this spike neural network, we did not have, this is unsupervised learning, right? So the STTP learning rule is unsupervised. And well, this is it. And if you have any questions, I'll be happy to answer them. Let me return to this.
Do we have any questions for Juan?
Doesn't look like you have any questions.
Yes, we have the first one. Can you see it?
Oh, they are writing on the, okay.
Yes.
Are there already direct applications of event cameras in industry? As far as I have seen for object tracking, very fast object tracking in conveyor layers, you will find these kinds of things. There are a few companies which are commercializing event cameras. One of them is a Prophecy in France, and there is also this Innovation, which is in Switzerland, and they are selling quite well all of these models. So I guess yeah, that there are some commercial applications for the cameras that are being out there. And also I know that Sony has developed their own DVS, their own event camera. I could imagine that for processing in very fast land conveyors, it will be a very useful technology, like object tracking, counting, and these kinds of applications. Any other question?
Okay, it seems we don't have more questions. So thank you very much for your presentation, Juan.
Thank you for the invitation. I wish you all wonderful sessions coming up in the summer school.
Thank you.